Okay, so this is a good time to step back and see some of the larger implications of the algorithms we've already seen. Okay, so even though none of the problems we've looked at is one that we'd want to solve in practice, the quantum algorithms we've already seen have a great bearing on some fundamental questions about computers. So for example, when we say that certain problems are easy or hard to solve on a computer, so problems like matrix multiplication or primality testing or factoring, what kind of computer do we have in mind when we say that these problems are easy or they're hard to solve on a computer? Well, it turns out that computer scientists and logicians thought long and hard about these questions and came to a remarkable conclusion that it doesn't really matter what the details of your model of computation is. That in fact, if you were to look at the most stripped down model of computation, the most bare bones model of computation, like a Turing machine, then this is already good enough. And this is what's encapsulated in what's called the extended Church-Turing thesis. What it says is, basically, if you could imagine the most sophisticated model of computation of what a computer would be, that you could actually reasonably implement in nature, and let's say that you can solve a problem in t steps on this hypothetical computer, then you could also implement it in some polynomial in t, so let's say order t squared steps, on this very bare bones computer called a model of a computer called a Turing machine. So what's this very bare bones model? Well, you have an infinite tape which records zeros and ones. There's a read-write head which is local and it can only see one of these tape squares. And then there's an internal control which is finite, which says, basically, which is a set of decision rules which say, if I'm in this state, I'm looking at a 0, I'll write a 1, I'll move one step to the right or one step to the left. There's a very nice way to interpret what a Turing machine is, which is to think of a Turing machine as describing the set of functions that are humanly computable. Meaning you think of this infinite tape as an infinite stack of paper, and the read-write head is a pencil or a pen. And so this is what a human being or a mathematician the functions that they could compute using pen and paper. There's another way to think about computation, to ask what can be physically computed. And there's a beautiful model called the cellular automaton, which seems to capture that. So in a cellular automaton, you have a grid of cells where each cell can be in one of a finite number of states. So in this case, black or white. And then in each step, each cell looks at the states of all its neighbors and itself. And based on a small set of rules, decides what its new state is going to be. So if it's white, it's surrounded by all black, it might change itself to being black. Or it might change itself to a majority of whatever its neighbors look like. So why is this in what sense is this a model of nature? Well, here's the sense in which it is. You see, in classical physics, you try to describe physics by local differential equations. And so what does this do? Well, basically what it says is, if you're at a point x, then you describe the new state of that point by saying, look at an infinitesimally small neighborhood around x And based on that infinitesimally small neighborhood, you say how the value of whatever physical quantity of interest you have, the magnetization or whatever else, changes as a function of the current value of that physical quantity in this small neighborhood. So a cellular automaton, which is what this is just a discrete version of that. And so in that sense, it's a model of everything that you could possibly imagine doing in nature. Because after all, because of noise, we cannot have infinite precision, and so we must have some level of granularity to the computer. And so the fact that a cellular automaton can be simulated by a Turing machine with only polynomial factor slowdown tells us that, in fact, from that, thinking about humans as computers or nature as a computer, it's all the same. We get the same class of functions that we can efficiently compute. Okay, so now what we've learned is that, in fact, quantum computers do not obey this extended Church-Turing thesis because they can solve certain problems faster than you can classically. So if you look at Simon's problem or recursive Fourier sampling, these do not satisfy the extended Church-Turing thesis. And so this really opens up these wonderful new questions about what can nature compute now? And is it possible that there's a quantum Church-Turing thesis which says that, in fact, if you have a quantum computer, that's the ultimate, that anything that nature can compute, you can always compute quickly on a quantum computer. It also leads to very interesting questions about quantum mechanics itself and what's the potential power of quantum mechanics. And so these are some questions we'll touch on in this course, but some of them go well beyond the scope of what we can cover in this course.